lesson 5. It's on differentiability and continuity. And the reasons these come back up is because these types of questions come back up very often. So we'll be looking at graphical characteristics and differentiability at a point. You'll need to recall the rules of continuity when you're justify a function as continuous. The first thing you'll need to do is figure out if f of a exists. Does it equal a number? If it does, that's great. Now, because we have those instances where we have functions and then we have a break and perhaps a hole at a function. So like we've had those instances where we have f of a exists, but the function itself is not continuous. So that's why this is how we justify these checks. So first, we find whether f of a exists, then we test both sides of the limit. So we need the right-hand limit, so the limits as x goes to a minus, it needs to equal the limit as x goes to a from the right, okay? Because we have instances where we might have a left-hand limit, but it equals this y value up here, and a right-hand limit, but it equals this y value down here. So we want to make sure these two exist. Once those two exist, it's just to prove continuity. The last thing we want to do is the limit of a function as x approaches a is equal to the function value at x equals a. So the last thing we want to check is, does that limit, because remember, if these two exist, then the limit of f of x as x approaches a exist. If they exist and they are the same thing, that is. So the last thing we want to check here is that this limit equals that point. Once that's true, we don't have to worry about breaks, and we justify a function being continuous. All right, so we're going to come back to this intermediate value theorem. I want to focus on the rules of continuity here, because in the first example, you're going to justify that this function is continuous at x equals 2. And it's just those three principles that I just outlined. And if you notice how much more easy it is to understand this, because those first times around, it is a little bit complicated. But unless you test yourself and practice, it doesn't get easier. So here we don't have to differentiate at all. What we need to do, this is based on the graph of f of x. If f of x is continuous at x equals 2. So explain your reasoning. So you're going to justify using those three principles. I will not do it for you, but you will need to check the following things. So here, a equals 2. So, or literally, it's your x value. So first I'm going to find f of 2. Does it exist? Question mark. The second thing that you need to find, does the limit as x goes to 2 of f of x exist? And the only way you'll know this, for sure, is you need to check. Does the limit as x goes to 2 from the left for f of x equal that limit as x goes to 2 from the right of f of x? Question mark. And lastly, number 3, if this limit does exist, does the limit as x goes to 2 of f of x equal f of 2? Do these two things equal? If they do, then this function is continuous. Your conclusion, if it meets all three, f of x is continuous at x equals 2. If it doesn't meet all three, then it's not. So this is either this one or that one. Just find, so you'll be working on that on your own. Just find the value of f prime of 2 to determine if f of x is differentiable at x equals 2. So just keep in mind shortcuts to this to make sure that you're on the right track. If you have if the function is at a point like this, where the two sides are different, there's some kind of corner, or there's a break in the graph, or what's the last one? Corners, breaks, and these cusp. It's not differentiable at this point. So once you figure that out, what it looks like graphically, you might could say yay or nay on differentiability. But if I'm going to do this, I need to find f prime of x, the derivative, and then I find f prime of 2. If there is no answer, then it does not exist. If there is an answer, then it is differentiable. Not differentiable. So you need to find that. Is differentiable. Okay? Moving on. Example 2, same type of problem. Okay? Now, just moving backwards to the intermediate value theorem, it says if f of x is continuous on a, b, on this interval, a, b, from a to b, and f of a is less than y, f of b less than y, and y is less than f of b, then there exists at least one value on a and b where a is less than c, less than b, such that f of c equals y. So this has to be on an increasing interval. That means that function needs to be going uphill for this to apply. Okay. Example 2, we're not going to go over. Example 3, we're not going to go over. Okay, so graphically, a function is not differentiable if a jump occurs in a function. That means there's a break, it's discontinuous. So at a point, and I want to be very specific about that, at a point. So if I have a graph, I'm going to create 3 graphs here so you can see. Okay, there's first graph, second graph, third graph. Okay, so my first graph, let's do a little curve here. Let's do a little curve. So here's my graph. There's a hole right here. Then here is, so this is a jump where it jumps from one to the other. So it's not differentiable at this point 2. It's differentiable here, but at 2, since those limits don't exist, the limit of 2 doesn't exist. It does for the left and right. It's not differentiable. So that's just a fact. That's just a fact, and it'll come back up in questions. The second type is if a corner is created, and functions specifically you need to be careful about are absolute value functions with that typically, but let's say I wanted to know whether a function was differentiable at 3. Well, if there's a corner at 3, it's not differentiable at that. Now, lastly, there are the cusp. So here's a cusp. It's just kind of concave in there. And let's say this is -1. Well, at the cusp, it's not differentiable. So it's not necessarily the whole function, it's just specific points on that function. In order for a function to be differentiable at x, then two things must be true. F of a must exist, and the limit as x goes to a for f of x must equal f of a. So it must meet those continuity rules. Okay. Example 4, it says consider the function, this piecewise function. Answer the following questions. Is g of x continuous at x equals 3? Well, if you evaluate, you'll have to evaluate and find both of these answers. You'll have to evaluate here, and then you'll have to evaluate here. Okay? And what that'll do is let you know whether it's continuous, or you could get that left hand limit as x goes to 3 from the left of f of x, and that would be square root of x plus 1. Does it equal, question mark, does it equal the limit as x goes to 3 from the right for 5 minus x, question mark. If these two equal, then a limit exists. If they don't equal, if these two equal, then a limit exists, right? Now, if they don't equal, you can end it right there. Now, if they do equal, you'll want to see, does g of 3 exist for each of these functions? And it kind of doesn't for this bottom one, because 3 is less than that, all these x values. So there's a hole at 3. The last thing you'll want to check is, does this limit as x goes to 3 for g of x equals g of 3? And that's only if the limit exists. If it doesn't, then you pretty much can stop there. Is it differentiable at 3? Well, if this is true, only if this is true. Okay? And then you can do your homework. So just to wrap things up, I'm going to go back and do this one. Okay? So I'm going to erase all of this, erase all of that. I'm going to graph this function first and show you what this justification looks like. So I hope you actually did it already, but I want to go through what this justification looks like. So first I'm going to graph this function. So here at 2, the square root of 0 is just 0. So right here, okay, 4, let's try 4, 1 is a negative number. It's not defined. It's not defined. So before this is not defined. Let's try 25 minus 4 is 21. Square root of that is approximately 4 something. So somewhere up here. Somewhere around there. Okay? So I'm going to create a little graph here. Okay. Okay. All right. So it says based on the graph, is f of x continuous at x equals 2? And so before it gets to 2, and that's a no. That's a no. Okay? And this is my reasoning. When I go to the limit rules. All right? So what I'm going to find is the limit as I go to 2 from the left does not exist. So the limit doesn't exist. So it's not continuous. So I know that f of 2 equals the square root of 2 squared minus 4. This just equals 0. All right. Now I know that this is true. So number 1, f of 2 exists. Okay. Number 2, does the left-hand limit exist? Okay. And so what I'm going to do is use a graphing calculator here. I think I have one on here. A4. Let's see here. Let's see, guys. All right, there we go. TI-84. And I'm going to go type that into my calculator here. So clear. So seconds square root of x squared minus 4. Okay. And already I've got some stuff that says it doesn't exist. Okay. So I'm going to go to the table. And if I look at 2, it's 0, right? But before that, it's not, it doesn't exist. Okay? So obviously graphically it's not continuous, and I didn't do this side of it. So it looks like it starts back up at -2. So let me go graph that on there. Anyways, so I need the limit as it gets closer and closer to 0 from the right, but on the left, it just obviously doesn't exist. So let's finish this. Let's finish this proof up. So, all right, this limit right here on the left does not exist, does not equal 0. This is approaching 0. Let me go ahead and graph this function. All right, there we go. All right, so that's my graph of this function. I'm going to label it just in case. Okay. So therefore, the limit as x goes to 2 for f of x does not exist. Okay. Since the limit doesn't exist, does not exist, the function is not continuous at x equals 2. Okay? It says find the value of f prime of 2 to determine if f of x is differentiable at x equals 2. So it's not differentiable because of this limit doesn't exist. But let's find the derivative. So that's d dx, and I'm going to write this as an exponential. Okay, so this equals 1/2 1/2, and then I need to differentiate what's inside. So I'm going to show me doing this right here. I need to differentiate what's inside. So I did the outside. This is the outside right here. Makes it a lot easier when you highlight. So this is going to be to the minus 1/2 right here with what everything inside. Okay. Now inside, derivative of x squared is 2x, and the derivative of -4 is 0. So this equals, this cancels, x over x squared minus 4. Now you can leave it like this, whatever you want to do. So f prime of 2 equals 2 over the square root of 2 squared minus 4, and this equals 2 over the square root of 4 minus 4. This equals 2 over 0, and the derivative does not exist. Therefore, it's not differentiable at 2. So you do need a concluding statement. Therefore, so since, basically write a statement, since f prime of 2 does not exist, f prime of x is not differentiable at x equals 2. Like, more than one answer here. You could have used this information from the limits to say that it's not differentiable, but this one's probably a little bit easier for people without having to go through a complicated statement. So I hope that helps. Like I said, please, please, please do all this work. Make sure you do all these pages, take pictures of them, turn them in, because it's a part of your work. Lastly, do your homework, take pictures of it, and turn it in to Schoology. It's based on everything that we just did. All right. And this is from Unit 2 and 1. Have a good day, guys.